I'm from the UK Education Funding Agency, and I'm going to talk about achieving thermal and acoustic comfort in classrooms in the UK. I want to take you through some design issues and some example buildings very quickly. We've got a London heat island which causes us some problems. It's 12 degrees hotter than other parts of England, and in those areas the conventional wisdom is to use exposed thermal mass. We've got to get acoustic absorption right as well, and it's quite difficult to do both in the same space sometimes in a classroom. But in cooler climates we needn't use the thermal mass in classrooms, and we've shown that ventilation can provide adequate summertime cooling, especially with using some thermal mass, for instance heavyweight plasterboard instead of normal weight plasterboard, and the weight in the floor, or even passive phase change materials. But exposed thermal mass can provide a very stable internal environment, so in a heat island it is a sort of ideal solution. The absorption in a room, acoustic absorption, has to be well distributed, and Shane was saying about how do you get the basic absorption well distributed when you've got a concrete soffit, and I think that's quite a difficult thing to do. And we also need to be wary about flutter echoes. So thermal comfort in cold weather is a big issue in English schools. In the 1960s, classroom radiators produced 160 watts per square metre, and there was quite a lot of leakage into the room. So there was diffused ventilation through the leakage with big radiators. There was not much problem with cold air. Now we've got very small classroom radiators, 60 watts per square metre. That's a maximum as well. It could be a lot less than that. That's insufficient heat to temper the incoming ventilation air. So we've got to find a way to get the air, when it reaches the occupied zone, comfortable enough. And we've introduced a new guideline which says that the occupied air, when it hits the occupied zone, supply air must be at least 15 degrees in a classroom. That's 5 degrees below the normal environmental temperature of the room. And that's where I'm trying to say that the thermal comfort criteria like ISO 7730 would say that isn't comfortable, but I would maintain that that is comfortable for children. So we need to look again at the metabolic rate of children, which is much higher than people think it is. We've got some studies from 1990 that show that children's metabolic rate is almost the same as an adult. That is unpublished, and there's a very big lack of work being done on the metabolic rate of children. But we can't use adult rates to design spaces for children. And we know that 15 degrees C works in practice. This shows the effect of cold dumping, as I call it. So even when you've got a high level inlet, you're letting in 256 litres per second of cold air. That could be 10 degrees C. It will dump. And the result of that will be people won't open the windows. We've got a very simple line plume calculator that's been developed in England, which estimates the cold dumping effect from different height openings at early design stage. So we can tell what height the openings have to be to give certain litres per second for the pupils. Now this was trying to explain why you've got quite a lot of high internal gains in a classroom. 30 pupils at 80 watts, or could be 100 watts each. So you've got a high load already in there. So when the outside temperature is below 5 degrees C is the only time you need to heat a classroom in England, and that happens only 30 days a year. If your heating system's going 200 plus days a year, you've got a lot of distribution losses and a lot of wasted heat. So simple, fast response systems are probably the best alternative for schools. Underfloor heating, I think we just mentioned that can cause a big problem because we've got the floor emitter slope 11 watts per square metre per degree C. So a floor of 27 degrees gives off 60 watts per square metre. When the class walks in, you get another 40 watts per square metre, and it soon takes the temperature up into the uncomfortable region. And because the thermal response time of the slab is very slow, so you really need to keep the temperature down below 26, and I'd recommend 23, so that it's a self-adjusting thermal mass system. So you've got 21, 20 degrees as the comfort temperature, 23 in the floor will just keep the room nicely topped up. But you do need an alternative heating system for the cold times, because people open the doors to outside. You know, primary nursery age children are in and out all the time, the door's open. So you need a very fast response, and that's where the radiant, metallic radiant panels are quite useful for nurseries. There we got a problem with asymmetric temperature difference criteria. The ISO standard talks about the difference in upward radiant temperature and downward radiant temperature, but it measures it at 600 mil off the floor. That is the wrong height, I'm absolutely sure, or pretty sure, when your temperature sensor in your neck and your head. What we need to talk about is the delta T plane radiant temperature looking upwards, the effect of the hot panel on your top of your head. If you get that right, you can ignore the asymmetric temperature difference, as long as you've got an insulated floor. So what we found is that ventilation air close to the ceiling is very useful, because it takes the heat out of the slab. If you trap a layer of air at the high level in a room, which happens with a lot of designs with low level windows, in summer you get the heat build up, you've got a highly insulated envelope, and the ceiling acts as a radiator and causes discomfort. So the old system of, this is of like a 1950s school, worked very well with cross ventilation in summer. I think that's probably a bit, do you want to see these as quick examples of? This is White Cross School. It's got timber insulated panel walls, and it's got concrete roofs, and it's basically a passive thermal structure. It's also got very good daylighting on the top floor, and it's got a mechanical heat recovery system, a very, very simple one, with a central heat recovery unit, but no controls at the classroom level, because that adds in sophistication which goes wrong in classrooms. So this was quite a while ago this was done, and it's got a highly efficient thermal wheel at the core of it. There's the central supply air duct, and it's extracted through the classroom doors, through the corridors and back. So it's a very simple, it's providing too much air though, it's 8 litres per second all the time, so it's actually probably too much. So we moved away from this now. It's got acoustic baffles, which it needs, you can see them on there. The slight problem with that is cleaning of those, I would suggest. Is that sort of dust traps, but this is a fairly, it's 90s design now, this is. But it did perform quite well. And the really impressive thing is the way it stabilizes the temperature. So there's the outside temperature going right up, but it's really constant, 26.5 when it's 33 outside. So that's the advantage of the thermal mass. There was some problems with it. The windows weren't opening easy enough. It didn't have proper weather lobbies to stop the heat going out of the building, and it didn't have room control. So we're now using CO2 control of the ventilation to reduce the amount of ventilation air that's heated up. So this is where we are now to 2015. We've got climate-based daylight modelling, so that's using simulation of the real sun and sky. That's led to a lot less glazing percentage and less solar gain into the classrooms. And we've got room-based CO2 and temperature control. We've got acoustic absorbers, either hanging absorbers or wings to light fittings, or a new one I've discovered is as part of the radiant panel, which is sort of what you've come up with as well. But these are just very conventional radiant panels. This is what we call a premixing system. So it's not a heat recovery. We don't have filters and heat recovery units. We're just mixing the room air with the incoming air to raise the temperature up above 15. And we've got a cloth duct to diffuse the air, so that it does not uncomfortable. And that's a very, very simple system with minimal maintenance. And it can be exposed in the room with an exposed slab and working with the night cooling as well. So that's it working in natural mode. This is called a Breathing Buildings Company solution. Summer mode with boost. And in winter operation, you've got the mixing so that you don't get the cold drafts. But you can still open the windows when you want. And when you open the windows, the CO2 demand knocks off the or sets back the ventilation. So I think you're right to say ventilation is the biggest problem in schools. It's not. It's a different situation because you've got 30 bodies in there. You know, it's quite a problem. This is the more conventional approach with a heat recovery unit. More maintenance.
Just natural ventilation from outside, bringing it in without heat recovery. That's also allowed within the energy regulation.
It will actually be more energy efficient over the year because this one has got more fan power. We've got 3 kilowatts of heat from the children. It's only 30 days a year when you actually need any heat. And the extra that you've got to put into the fan to make this work through the filters, it's got 2 fans instead of 1. So this actually works out more energy inefficient than the previous system.
Calculate with our regulation the energy performance of school buildings. Always have to implement heat recovery.
Yes, well,
Otherwise you don't meet the requirements.
yes. What you get with a premixing system is heat recovery, but it's just not allowed for in the software. The standard software doesn't allow for it. You have to work the software allowing for the heat recovery from the people because we're not throwing it away. It's in the room, so it's not conventional heat recovery. Yeah, and maybe our standards aren't as high as yours. These are theoretical. The trouble with that idea is that energy is so cheap, you're paying such a maintenance cost. The maintenance will cost you more than the energy you've saved.
And then you look at the cost of energy you pay for, not refine that.
That's right. Yeah. Although if this is less efficient than the other system, it's a problem with the software, I'd say. I mean, we know that our Part L in England is way out of. I don't trust those calculations anymore. So CO2 demand control is a very good energy saving part of this. That's quickly going through. These are just quick examples of absorbers. Very ugly absorbers. Fairly ugly ones. Quite nice ones. So you can make them look nice. I was trying to show. It's plonked on the walls. It's interesting. Very ugly ones, I'd say. And this is a combined radiant and acoustic panel, which I just come across, where this is the acoustic performance of that panel, and I'll just give you a quick picture of it. It's got acoustic absorption on the back, and it's got the holes on the front, and it's got the tube, so it's trying to do both. It's a very simple radiant system. And then I do have this problem with the comfort temperatures, so I think we need to go to BS 7726 and talk about the difference in plain radiant temperature instead of asymmetric temperature difference, which is what the ISO standard asks you for. And that might have wider application in that I believe the comfort temperature at head level is important, not at 600 off the floor. So I think maybe there is something that needs looking at in the comfort standards. These are those perforated panels. Just a couple of references. That's our website on lighting, acoustic and vent. There's a British standard for 772X, which is in this Riva guide. It's full of these. All the standards are in here actually at the back. So this has got all the references you need if you want to get into this subject. Thanks. That's me, I think.